Okay, hi everybody. Welcome to lecture 10 of CMP208. It's about 3D audio, and for the first time this is a recorded lecture thanks to the cessation of face-to-face lecturing at the university. I'm hiding in my bunker and recording this one for you. I'm just intend to run through the slides as if I was presenting them live, but I'll use the mouse cursor instead of the laser pointer, and we'll just run through the slides as usual. So the agenda for this week, I've got a few observations from last week's labs, which actually went quite well, I thought, especially the first one. I walked into just a cacophony of bleeps, which was good to see and hear. We'll talk a little bit about 3D audio basics, particularly the maths that are involved, which is probably a good recap on some of just basic 3D math concepts. We'll talk about the 3D audio system, the stuff that the labs do, the system available in the labs this week does. I think it's quite actually an interesting system to think about, and that it's quite applicable to game programming in general, and that some of the concepts like emitters and a system which tracks the lifetime of some entity and implements its behaviour, those are quite generic things to do in gameplay programming, so I think it's a good system to look at. Much like last week's lecture, rather than spend time running through the code in the lecture, because I think that's better left for the lab, instead we'll speak about potential improvements, so things that you could do to elevate the system beyond what the bare minimum would give you. And that's always an interesting thing for coders to think about, because quite often when you make a game, you're looking for a few USPs, for unique selling points, for things that you can speak to a press outlet about, which just get people excited and give you something to enthuse over. And an audio system can potentially give some stuff there which, when you talk about it, people can get excited. And we'll talk about this week's labs. We'll talk about what's in there, the content, but also the fact that you won't be in the Vita labs this week doing them, so we might just have to see how that goes as the week progresses. The module surveys are also out, so I'll just prompt you to go there and fill that out. And as always, we're happy to take questions. Obviously there's nobody here just now, so there won't be any actual question time, but any questions on this stuff, feel free to message us. You can either email myself or Chris, or we'll put some kind of more instantaneous communication in place for during the labs. So observations from the labs. Obviously we tried that change in the lab notes with the 4 different people who are quite representative of what you might meet in the games industry, and giving you the problem in different levels of detail. I thought that looked like it went quite well, but obviously I'm willing to reconsider that based on feedback. So again, just feel free to let us know how that worked for you, whether you felt that you could accomplish it through the small level of detail, or whether you had to run through to the lecturer towards the end. I'm just interested to know. I've written this week's labs in the same way, so I'm kind of assuming that it worked, but please let me know if that's not the case. A couple of bugs we saw in the labs last week were related to floating point. And floating point is slightly counterintuitive, and I think this video here does a good job in explaining why. But what it really boils down to is that you can't do equality checks on floating point numbers, so you can't say if this floating point number is equal to 0, and it's because of the way that the floating point value is represented in the hardware, as this video will explain. So just have a look at that, and remember that if you're using floating points, you're usually checking if they're higher or lower than a value, and not if they're exactly a value. And finally, the most common bug was just the set pitch. It can't actually be called each frame, That's maybe not behaviour that I would expect if I was using an audio library. I'd expect to be able to call set pitch dynamically all the time. But in this case, I think it was setting the sample back to the start, the music sample, and the start of the music sample was silent, so people were just getting no music whatsoever when they called set pitch. So it's not really a problem with what people were doing, it's more a problem with the Jeff. But at the same time, if you are experiencing something like that, you want to have a think about what you could change to uncover the problem, to illuminate it for you. And cutting it down to one set pitch call per, at a time is certainly something that you would want to consider. So moving on to 3D audio basics, we're just looking at a simple system so far. We're just loading in samples and playing them, looping them, changing the volume and pan or the pitch on the music, although you can actually change the pitch on regular samples as well. So just with that basic functionality, is it enough to let us approximate a 3D effect, and how would we go about doing that? So I'm really going to be looking at the volume and pan here, and first we'll deal with the volume. So if we've got the emitter here, if you look at this circle representing the emitter with the dot in the middle, although in 3D space you want to imagine this as a sphere, we're just looking at it in the XY plane. And as you approach the edge of the sphere, the volume's getting quieter. This is like the horizon of where you can hear the sound from. If the listener is just outside, then the volume is 0. As you move in, the volume will just creep above 0 and it will increase towards 1 at the emitter. And that's really the essence of what we're doing there. You might want to think about whether it's a linear increase or decrease. But for now, we'll just say that we need to know how far away the listener is from the emitter, and we need to compare that to the radius of the emitter to determine what volume we want to play that sample at. So how do we calculate the distance away? Well, we use Pythagoras. So this is a 3-dimensional implementation of Pythagoras. But if you look here now, 2 dimensions. If you imagine a triangle here, so this is the vector we're trying to find the length of. If you imagine extending out in the x to this point here, and then extending down in the y, there, that would be your 2 sides of the triangle, and this is the hypotenuse. So you've got your a here, your b here. A squared plus b squared is c squared. So if you take the square root of a squared plus b squared, you get c, or the distance. So here, remember, x2 minus x1, that's like basically going from here to here in the x. So that's the length in x, the length in y, the length in z, all squared, and then taking the square root of it. So yeah, when you're finding distance, you're thinking Pythagoras. I have seen a few students in the labs, not in our labs actually, but in other labs I was helping out at. They used the dot product here. They took the dot product of this vector with itself and then took the square root of that to get the distance. Now that works, but I think it doesn't speak to a great maybe understanding of what the underlying maths is doing. I think if you think Pythagoras instead, you're on more solid footing of understanding what we're doing in the 3D math space. I mean, effectively, if you do the dot product of something with itself, you're doing x times x plus y times y plus z times z. So it is the same thing, but I think you're maybe doing that encourages you to find functions that work rather than finding the mathematical explanation for what you're doing. So, but that should give us the distance, and then, like I say, we compare the distance with the radius, and we increase the volume as it gets closer. So the second part, once we've got the volume, we need to determine the pan. And the pan is just how much of the audio comes out the left speaker or the right speaker. And as it pans across from right to left, more comes out the left instead of the right. So instead of looking at distance here, because we've already used the distance for the volume calculation, here we're trying to figure out which side of the listener the emitter is on. So I think we need to change the the diagram here a little bit and think about it from the listener's point of view, and think about where the emitter is in relation to the listener. So that's what we have here. You can see the little white cross maybe has moved to the middle, and the emitter is here. It's on the right hand side, slightly to the rear. Now the reason that the listener is represented as this circle with two colours is just to reinforce this idea that what we're wanting to do is really figure out whether it's on the left hand side or the right hand side. And so we need some kind of mathematical function that's going to allow us to see if something's on one side or the other. And so what we would tend to use there is the dot product. So the dot product, if we take the angle between two vectors, if that angle is in degrees, if it's minus 90 to plus 90, we're going to have a positive dot product. So that would be, imagine a vector here extending forward, and then you're comparing it with any vector in this hemisphere here, or this semicircle here. Then all those are going to return a positive dot product. If your vector that you're comparing this vector here with is in this semicircle here, you're going to get a negative dot product. I think for gameplay programmers this is a very common use of the dot product, is we're only really interested in whether it's left or right. We're not so interested in comparing it against a value, although I have seen it for maybe field of view checks for like AI, as a guard is scanning, you might want to check against check it against an angle, so we might want to actually find out the angle and compare it. But in general, we quite often use the dot product just to say, is it in front or is it behind? And that's comparing it with our forward vector, but we want to know, is this to the left or to the right? So we don't compare this with the forward vector, we use the right vector of the listener. Again, this is quite a common operation. So we have the right vector here. Now that will probably be available in the listener. If the listener is represented by some kind of transform, you'll just be able to extract the right vector from the transform matrix. So we get the right vector, and then we compare the emitter to listener vector with that. And if it's positive, then it's on the right hand side. If it's negative, it's on the left hand side. So that's quite straightforward, but the only other thing that we really have to think about when we're doing this, which we didn't have to think about with the volume calculation, is that this is also directional. So if we turn the listener around, so the listener is facing downwards, then suddenly the emitter is on the left hand side and slightly to the fore. It's not on the right hand side, slightly to the rear. So the PAM calculation is wrong here, unless we somehow orientate, as we reorientate the listener, we have to reorientate the emitter in their space. So again, we need to think through our maths library and think what we've got, which would maybe allow us to do this. So as we turn this listener round, or as we bring this listener back here, this emitter would have to go around with it to be in the correct space for us to make our calculation. Yeah, so essentially what we're trying to do is we're wanting to convert the emitter world position into a listener local position. So here we have the initial state where the listener is facing, backwards, downwards, and the emitter is to the left of them, and then we reorientate the listener into facing forwards or a neutral position, and that emitter has to be rotated round so it's still to the left and slightly forward of them. So how do we move the emitter into the listener local space? Well, we need to use the inverse transform of the listener. So if you imagine here, this is the starting positioner for a listener, it's at the origin, it's not orientated, and then through gameplay it gets orientated this way. Then its transform is representing a 180 degrees rotation in the Z in this case. It's facing backwards. If we want to reset it to here, we need to take the inverse of the transform that took it to here. So the inverse of the transform will reset the listener back to the origin, And if we also multiply the emitter's world space by that inverse transform, then that emitter will be orientated correctly relative to the listener. And that's what you're seeing here. Yeah, the emitter position, the local position for the emitter, is the world position for the emitter times the inverse transform of the listener. Hopefully that makes sense to you. I think that's the trickiest bit of maths here. But really think about the matrix that describes where the listener currently is, and then think about the inverse matrix being one that would almost return that back to a default orientation at the origin. And then think about, if you used that matrix, if you applied it to things that were around the listener in world space, how they would end up in listener local space at the origin. Okay, so hopefully that's okay. I think that's, like I say, the trickiest part. So maybe we can get on to something a little simpler now, which is the 3D audio system itself. So this is a typical audio scene here. You've got the listener here, the little white cross, and it's moving between a number of audio emitters. It's well within the horizon of the red one, so it'll be listening to that. It's right on the cusp of hearing the green emitter here, and then the slightly lighter green emitter is out of range. So this is the kind of thing we're looking at. So already we're getting some names for the objects that we're going to create for our system. We're definitely going to have listener. We're going to have a number of emitters, so we want to store them in some sort of container. And so that's what the 3D audio system needs to do. It needs to maintain the listener, maintain a collection of emitters, and then it's responsible for starting and stopping sounds, maybe as the listener moves in and out of range of the emitters. Quite interesting there to think about what happens if you move part way through a sound. So I think the simple system as it stands is just looping or playing effects constantly, so it doesn't have that problem. But if you imagine someone talking and you move out of range of them and then you come back into range, you can't really have stopped that effect and then restart it when it comes back up. It has to come back at a reasonable point during that speech. And it's also, as we were just mentioning there, it's going to calculate the correct volume and pan of all the playing sounds to allow the player to feel like they're moving in a 3D space. So the first object we're creating, I guess, is the emitter. So if you think about what an emitter requires, it requires that position, which is something that your sound sample, when it was playing, it didn't require. But because we're going to be calculating this in 3D space, we need to give the emitter a position. Just like you did before, it's going to have a sound effect ID, which you get from loading the sample in. That sound effect ID could be shared across multiple emitters. You might have lots of people firing rifles and they all share the same rifle sound effect, but they will have unique voice ID for each time that's played, unless it's looping. And also you might have some status indicators, like is this a looping noise and is it currently playing. You also have a listener, which for our case just now, the listener really just needs to know its position, its transform. And we would probably, because we're going to use it quite frequently, we might also calculate the inverse transform at the same time that you set the transform. There are other ways you could do this. You could say that you only calculate the inverse transform the first time it's required, so if there's actually any sounds in range. But I think for most games you're going to have a lot of sounds playing, you're going to regularly be hearing audio, so it would make sense that at the point you set the transform you also calculate the inverse transform, and it's there available for any calculations you want to do with your sound later on. And here's a UML diagram just showing you some of the relationships there and the type of methods that you have available in these classes. Audio 3D is the 3D system itself. I don't think we've mentioned that yet. I know I badmouthed UML diagrams in a previous lecture, but they can be useful for showing these types of relationships where the audio 3D will just have one listener but it'll have many emitters. That might be what the double arrow indicates. I'm not entirely sure. UML didn't come up much during my my career, but we'll certainly have a lot of emitters, and we'll be updating these, and we'll have one listener moving through it. And here's a little bit of pseudocode just describing what the system does. It loops through the emitters, it calculates how far the emitter is from the listener, and then if it's in range, it takes responsibility for starting the sound, or and then also calculating the emitter volume, pan, and setting those on the sample. As I mentioned there, this is slightly maybe slightly strange in that some of this updating of the emitter depends on how close the listener is. So just that strange situation where the system starts and stops the sounds playing based on whether the listener's in range. That might cause a few problems depending on what kind of game you are making. I've also got a question in the lab notes which relates to this a little bit. So the question on why does Corinne have so many emitters, or more emitters than she expects to have in her test scene? I think that's to do with this idea that the emitter behaviour and lifetime is dependent on the listener's movement through the scene, which seems a little bit off to me. So that's something to read about once you've got familiar with the code. Finally, if you move out of range, then it stops the sound on the emitter as well. So I mean, that's pretty simple what we're doing here. If you've understood the first part of the maths, you'll get this block of it here, and then the rest is really just about the management of the emitter and the playing sound itself. So that's the basis of a system, a very basic system. So what could we be thinking about if we are an audio programmer, and we're thinking about how to elevate this system? You know, we only have one listener. We don't think about the surrounding environment. We only pan it from left speaker to right speaker. So some systems we work on might be more complex than that. Although the audio library that you're using might, remove you from that, so that you're not having to consider that too much. And for many games, you won't have to think about any of this stuff. Some of the games I showed last week on mobile, they didn't really even have the concept of a listener position. They just played the audio. So you might find that you don't end up doing any of this kind of stuff, but some games will deserve a more sophisticated treatment of their audio system. So we'll just look at some ideas there. The first thing that came up in my mind when I was thinking about audio is this binaural recording. A friend, he's got one of these microphones. He runs an audio business, and so it's always on my mind the possibilities with it. But essentially what it does here is you've got the dummy head here, and the microphones are actually placed inside its ears, and that really allows the recording of audio to simulate what is happening when you're hearing sounds. So you've got the head, which creates a bit of a shadow when the audio arrives from one side. It arrives in one ear slightly before the other, and the head has changed the way that this audio has entered the ear on the far side. So there's a slight difference between the two there, whereas on our system we treat the listener just like a pinpoint. So we don't have this concept of something maybe obscuring the left channel from the right. You've also got the ear shape itself, which the way the sound bounces around and comes into the ear, that's going to change the recording a little bit. And so a lot of this is dependent on where the object is when it's being recorded in relation to the dummy head. And what that makes it difficult for an audio programmer is that you're not going to be able to just record audio from all kinds of different positions. So you're going to have to think about how you would simulate that, essentially. Quite a difficult problem. There's a little YouTube video here. It's a BBC Click thing, which is, it shows a BBC team who've been working on this kind of problem, and they've created a game. So it gives you a little bit of a look at that. This is probably something that would really require a deep collaboration between an audio designer and an audio programmer to really realise in a game, and it's not something I came across in the games I was making. Much more likely in the games you're making is this concept of line of sight. So our really simple engine, it only thinks about how far the emitter is away. It doesn't think about what's between it and the emitter. So, you know, you're going to end up in lots of situations where you might have a sound effect that happens very close to you, but there's a wall in the way, thick stone wall. So it obviously shouldn't play at the same volume as it did in air. I've put a little example here of, this example is the Metal Gear Solid 1. So it's the entry level of that when you arrive at the docks, I think, and you have these large shipping crates and you're moving between them. There's a little mechanic where you can rap on the shipping crate to alert guards to come and look at, or to distract them so you can move behind them. And this was back in PlayStation 1 days, so they weren't doing anything too complex. But nowadays that would be an opportunity, I think, to think about how sound propagates and sound echoes with different environmental concerns around it. And maybe you could do something quite interesting there with how people get distracted and where they perceive that the sound is coming from. Obviously it was a great game as well, but a real kind of game changer. So if you're actually implementing this, you're going to be thinking about what can you do, again, using your toolkit of maths and gameplay elements. And the two that come to my mind are just doing lots of line of sight checks, so doing a line of sight check to the emitter, and then if you're obscured by stuff, then maybe looking to do a little simple route find to find if there's a path there which would allow the sound to travel to you, maybe in a different way. And I think that's what this video shows here. This video is doing something like that, where it's, you know, if you're if there's a wall in the way, it'll look for the doors and it'll see if it can get line of sight to the door and then to the emitter, and then it'll use that to modify the volume, the reverb and the low pass filter, so when you move outside you'll get a different level of reverb, and if you're listening to it bouncing off walls and so on, you'll get a more, you know, they'll run the low pass filter and you won't have as much high end frequency. Another thing that I've done before is just creating audio regions, and some of the route finding would be encapsulated in this, but you would have an audio region which would allow you to set some parameters on the audio. So again, just looking at reverb or muffling it or so on, and that puts a lot more responsibility onto the audio designer or the game designer, potentially, to mark up a lot of information. So you're almost just inquiring as an audio programmer, you're inquiring from these regions whether you can hear a sound that's being played and how that sound should be played to you. I'm not sure what you would call that if you were looking for it, but I think some kind of rich contextual markup of the environment is what you're looking for there, and then maybe you have to do fewer calculations as the audio programmer. And then also interesting to me, if I was making a system, is just what you do if the emitter is moving quickly. And maybe this comes from working on racing games quite a lot. And so I'm thinking Doppler effect. So if the emitter is moving very quickly towards the listener will hear the sound at a higher frequency, and if it's moving away at high speed, the frequency will drop. Or if the listeners are moving. But yeah, so this velocity of emitters and listeners is quite interesting. It's very prominent in motorsport, but really only if you've maybe crashed or if you're looking at it from trackside. So I've got a little video here just showing it in case anybody's not too familiar with the Doppler effect. If you're usually in a motorsport game, if you're in a car and you're racing against other cars roughly doing the same speed, you're not going to experience it to the same degree. OpenAL does allow you to set the velocity of emitter, so that's one big difference between that and the simple system that we're looking at. And I think it really just uses that velocity to calculate potential Doppler effects. It doesn't use it for other calculations. And I did find this little bit just when I was looking up this, where Lord Rayleigh observed that if a sound is moving towards the observer at twice the speed of sound, a musical piece emitted by that source will be heard in correct time and tune but backwards. So if you can get your head around that, you're probably ready to start implementing some cool Doppler effects in your game. And also relating to the speed of sound, I was thinking a little bit about just the delay and propagation of sound, which isn't something I've experienced that often in games, but I'm sure the more realistic sims must implement it. So if you just think about a sniper firing a supersonic bullet from over a kilometre away, you'll see the flash almost immediately. You know, the speed of light, very fast, it will be there. The bullet will arrive in under a second, potentially, at a high muzzle velocity. But the sound of the gunfire should take around 3 seconds to arrive, and that's a very, very noticeable delay. This is quite awkward to implement when you think about it. It's far easier if the sound's just relayed instantaneously to all the listeners. OpenAL doesn't attempt to do this. I think you could do something involving expanding horizon of the effect as the sound's played. Still quite complex if you're maybe entering that horizon at high speed yourself partway through that sound being played and just calculating the right time for it to, the right part of the audio to be played. But I would also say that maybe the player doesn't really expect these things either. I think in movies you would tend to hear the gunshot before you hear any like bullets whistling past you. So people don't experience that much in real life, so you're almost conditioned to expect to hear the gunfire. And when I look in games like this game here, it's got some just interesting footage of them collecting the audio samples, but then it shows it integrated into the game, and it's quite short range, so there's no perceived delay there. But I'm not sure I would expect to see much of a delay if I was the player. It would just maybe feel a little bit strange, so you might end up not having to do that. But if you're working on a more realistic sim with longer ranges, maybe a tank fire game as well, where you're maybe operating at a few kilometres, then it'd be something you maybe have to put in there. I probably need to look at World of Tanks and see what they do. So this week, this has changed quite a lot from when I put this slide together. So yeah, I mean the plan in this week's labs was really to look at the 3D audio engine, try to extend it slightly so it wasn't asking you to do a lot of work, but also think about that system itself. So there was some more like conceptual questions in the labs as well. It's worth pointing out that the audio system only works on Vita, and as we won't be in the Vita labs, you won't currently be able to do this. So I think this is a better opportunity probably to work on your game idea, and then myself and Chris will look at getting some PC support for the audio, and that would allow you to play around with this a little bit more easily. Worth remembering, your assessment also doesn't require 3D audio, so if you find that you're not able to dedicate as much time to this lab as you would have to the others, then that won't impact on your assessment as much. But I do think there is a lot of value in this week's stuff, just in relating to general gameplay programming. Term 2 module surveys are open. You've probably seen the notification on my Abertay. Student feedback is important. I've been trying to do a few slightly different things as we've moved through the lectures and labs this semester. So I'm particularly interested in feedback on code demonstration, the level of information we give you going into the labs. That's something I've really struggled with a little bit, to find the right level, and that I don't want people to go to labs and just copy out code and think that they've maybe assimilated the lesson of the lab. I think it's much more important to sit down and read through the code, read through the library, and try and figure out what you can do to make that work, see how the code speaks to you. But yeah, anything you want to feedback on there. Apparently it's got 27 multiple choice questions. Be specific, be realistic, focus on the issue, not the person or the people, in this case me and Chris. Keep it relevant, provide suggestions for improvement. So yeah, if you get a chance, fill that out. Hopefully this week's shutdown hasn't clouded your perception of the module too badly. And I think that's it for just now. I think I've run through that a little bit more quickly than I would in a lecture situation. There are a few YouTube videos there for you to look at as well, and just think about what they mean for your system. Okay, I won't see you in labs this week, but any questions, feel free to email us, and we'll try and set up a more instantaneous method of communication for the scheduled lab times this week. Okay, thanks.